Okay, so basically what we're going to talk about is raster analysis tonight. We're going to break the lecture up into two parts. The first is sort of an overview about raster data in general, and the second is about all the different types of raster analysis that are available in ArcGIS. And we're only going to cover, well, just a bit of it. There's really a lot you can do. So first, we just want to make sure that we're all on the same page and understand what we're talking about when we talk about raster data. So, as I did in class many times, make the examples about the tiles on the floor, about how raster data is simply a grid of evenly spaced squares, if you will, XY basis, nothing really complicated. To take that data and place it on the Earth, it's simply a matter of geolocating that upper left-hand corner and then, boom, placing it. Raster data is based off of pixels or cells. Each pixel contains one value, one number. The dimensions of pixels vary, okay? This is what we call resolution. And so even though the system is entirely grid-based, it's entirely pixel or cell-based, the size of the cells could be any size you want. In this example here, for purposes we're looking at this, they're saying this is a 30-meter grid or a 30-meter cell. And that would basically mean that that particular pixel or cell in the raster equates to a 30-meter by 30-meter square on the ground. And so within that cell, there's going to be a number that represents some value. For example, it could be elevation or rainfall. They use examples. Now, rasters, these values should be integers or floating point numbers. Unlike a polygon, each of these cells only has one attribute, its value. And so if you need to have multiple values, that means you have to have multiple rasters. Most raster formats are binary in nature, stores things as ones and zeros, and this sort of gives you an idea of how it calculates out to figure out what it is. The part, excuse me, you need to remember is the number of bytes, 8-bit, 16-bit, reflects the range of values, the size of the numbers you can have, and that can create a problem. If, for example, you're looking at something that's in a number that's greater than 65,000 and you're trying to use a 16-bit setup, that's a problem. Or if you're trying to deal with something up in the thousands and you're using an 8-bit, that's a problem. We talk about pixel depth, the number of bytes used for each pixel. More bytes means larger numbers, means more space. When we look at integers, like we were talking about on the previous page, 11-bit, 0 to 255, 16-bit, up to 65,000, 24-bit, 16 million. Floating point, if you're going to have decimals, that's what you have to have. 32-bit pixels is basically 4 bytes. Now, floating point can create problems because floating point values don't like to create attribute tables. Raster attribute tables tend to like to generate whole numbers. But there's ways to do a lot of these things, and I'll show you some of those tricks either in this class or the next. So, what are some of the types of rasters that are out there that we use? We can use it to identify land use. In this example is a discrete raster. And a discrete raster is something where values don't change frequently, but when they change abruptly. In other words, you're one thing until you become something else. You're land cover 10 until you move into what is then land cover 14. Simple as that. You can also use this to do approximation of lines like roads. In this example, the road is represented by a connected set of pixels. And then you have continuous rasters where basically you have a cell for everything in the area that records one bit of information, and that can be elevation or what have you. or it could be color values for an image. When you go to the layer properties and you look at the source with raster data, you'll see the number of rows and columns, the number of bands, the cell size, the format, the source, the pixel depth and type, and all that stuff is there. And if you want more information, you can literally just scroll down. I want to talk a little bit about bands. I'm a big proponent of 80s music. Hair bands are pretty popular, but that's not the kind of bands we're talking about here. What we're talking about is raster bands. Raster bands is a little bit tricky. We tell you that rasters can only have one bit of information in each cell, and that's true. What they can have is multiple bands of information. A band is like a raster. It's like another raster. And so if you have a raster that has 7 different bands, it's literally like having one raster that you're looking at, but inside of that raster there's 7 different rasters, each of those representing a particular frequency or something, or color or what have you. And then within that band it has the values associated with that. And a typical configuration for something like this would be to take an image, a satellite image, and we'll just say you've only got 3 bands. One's red, one's green, and one's blue. If you want to look at those individually, you can, but to look at all of it together as a color image, you would combine red, green, and blue, and then you would get the color image. 7 bands, pretty common setup. There's different combinations that you can use of that, where it would give you things like certain false colors and other unique combinations that you'll learn about in remote sensing. So if rasters can only store, one bit of information, and they're kind of square and grainy and pixelated, why do we use them? Well, they're actually better for storing certain kinds of data, and they're better for analyzing certain kinds of data, and for some analysis, they're often faster than what it is for vectors. Imagery is the main one, because imagery is desirable for certain maps, and if you need it, you got to, this is what you got to work with. But there are drawbacks to rasters. The coordinate precision is generally lower. If you have a higher precision, it leads to an exponentially higher storage cost. In other words, as you go from like a 30 meter down to a 3 meter DEM, that is a humongous increase in the amount of data that you have to store. I mean, think about it. If you have a 30 meter grid and you drop it to a 3 meter, that means that for every cell you had in the other one, just by making that change of 10 in terms of the distance, that means for every cell that you had before that was 30 by 30, you now have 100 cells that are 3 by 3. So you see how it really amps up the volume of data significantly. And of course, like I said, the biggest drawback, you can't store multiple attributes. Raster resolution is measured by the cell dimensions. Storage space increases as the square of the resolution. So you go from 30 to 3, you went a change of 10-fold. 10 squared is 100, 100 times the data. So what does this kind of look like? Well, here we have some vector data, and then we have the same data, but in a raster format. With a 200 meter raster, it looks really bad. You go down to a 50 meter raster, it looks a lot better, but to go from a 200 to a 50, that's a 16-fold increase in the size of that data set. And that is a problem. Cell size, cell XY units are based on the raster's coordinate system definition. If you're in a geographic coordinate system, this gets really weird because it's based off of angular degrees. And so, if I've said it once, I've said it 1,000 times. Never, ever, ever do any kind of analysis in a geographic coordinate system. So just always project your data, and then you won't have to deal with trying to figure out what a 0.06 angular degree grid means. Okay? Project it, it'll be in meters or feet.